Good evening and good morning, everyone. My name is Salah, a researcher at Yiwen AAP, and I'm going to host this TrustML seminar about black box adversary attacks. But before that, allow me to briefly introduce Yiwen AAP to our valuable guests. The full name of the center is Yiwen Center for Advanced Intelligence Projects, AAP. It was founded in 2016 as the research center for mixed AAP projects, and it conducts Japan's leading AI research. This research center is headed by Professor Matashi Sugiyama, and it aims to enhance AI fundamental technology and its real-world applications. Our center encourages collaboration with various researchers around the world and engineers in related fields, and we'll be very grateful if you could visit us in our Nihonbashi office in Tokyo in the near future. This is the 55th Trust Scientist Seminar, and even if the recording is available online, please get in touch with the speaker before using any content. And today we are welcoming Yiwen, who's going to talk about adversarial attacks in black box physics. And Dr. Go, I have the floor. And thank you very much again for joining today.
Okay, today I'm going to talk about a little bit about black box adversarial examples. As you can see that a machine learning model, for example, a deep neural network, which was trained to classify images, could be attacked by adding some imperceptible but well-optimized perturbations to the input of the model to fool the model for making any incorrect predictions of the image. The perturbation, we normally call it adversarial perturbation, and the image with the perturbation is normally called the adversarial example. There are several different ways of generating adversarial examples given the model. Here I've listed two of the formulations. For example, we can maximize the prediction loss of the adversarial example by constraining the LP norm of the perturbation. Solving the optimization problem with such a formulation is straightforward. We can easily achieve the goal by using like projected gradient descent and backpropagation for calculate the gradient. But by using the backpropagation and projected gradient descent, we normally assume that the architecture and the parameters of the victim model are both known to the attacker. However, in practical scenarios, this assumption is too strong, and normally we don't know the architecture and the parameters of the victim model. Consider this setting, an attacker aims to attack a face recognition system powered by MACV or Clarify, which is online. Yet we have nothing known about the architecture nor the parameters of the model. So how to achieve the goal? I'll directly show the answer due to the time limit. Okay, comparing the white box environment and the black box environment, the main difference lies in the fact that in a black box setting, we don't have the opportunity to calculate gradient using backpropagation, since the architecture and parameters are both unknown. But we can take advantage of some black box optimization methods to somehow approximate the gradient or search along some promising directions to increase the loss of the victim model. Consider that both MACV and Clarify.com provide open APIs for new users, so we can somehow to take these open APIs as attack targets and generate adversarial examples. The generated adversarial example will probably also fail the online system because the online system probably use the same technology as used by the open APIs. The open APIs take image as inputs and output some predictions with confidence level. So we normally can get the input and the output of the open APIs, which enables black box optimization. the foundation of black box optimization and the so-called query-based method is the finite difference method. The finite difference method is derived from the definition of gradient. For estimating each entry of the gradient, we can use the formulation given in the slides, which means we can query the victim model twice to get the fx plus HEI and fx minus HEI to evaluate the gradient on the gradient at that place. But there's a main drawback of this method. We need to query twice for estimating each entry of the gradient. So for estimating the gradient whose dimensionality is just equal to the dimensionality of image, we need to query like 2 times the dimensionality of the image, which is very computationally high and costly. So so the main work in this line of work is just to reduce the cost of reduce the cost of query times. Okay. One technology that enables to reduce the cost of query is to take advantage of this approximation. It says that if we limit the search directions under a prior distribution, then we can approximate the formulation of the finite difference method with using the search time of t with t guide of search directions. Okay, so by using this approximation, we can reduce the query cost from 2 times dimension of image to just t. Okay, one question here is how do we decide the UT and how do we decide all these TUTs? One of our prior work proposed to utilize the similarity of different machine learning models. Like, for example, we can assume that the gradient of many different machine learning models, especially deep neural networks, form a low dimensional space. The dimensionality of such a space should be much lower than the dimensionality of the image space. Okay, because the representation and the gradient of different models should be kind of similar. Okay, so if we can collect some open source face recognition models online, or maybe even some open source ImageNet models online, we can somehow to form such a subspace with lower dimensionality. And to obtain each UT here, we can simply use the gradient on one of these models. Okay, here's the experimental results. We can see that with only 18 queries, the failure rate of such attack can be reduced to lower than 20%, while the baseline, the failure rate of the baseline is still higher than 60%. So the improvement is significant. Okay, so what's next? After this work, we review the query-based method and black box optimization methods by reconsider the way of generating black box adversary examples. We found that generating black box adversary examples using black box optimization is kind of like what we human beings do, what we human beings are doing every day. For example, we do planning and decision makings every day. While for generating adversary examples, we need to decide directions to search, like in each iteration, which is kind of similar. So by bridging the decision making process to the generation of black box adversary examples, we further bridge the gap. We further connect the way of generating adversary examples with reinforcement learning. So in this figure, we consider the the way of the task of generating black box adversary examples, just like playing in an unknown environment as a player, just like in the reinforcement learning task. The attacker here acts as a player in the environment, and it has to interact with the black box model, which is similar to, which is just like the environment in the reinforcement learning task. And the task of the attacker is to do some queries and actually as fewer queries as possible to successfully attack the victim model. Okay, which is just like we do actions and get reward from the environment in reinforcement learning. Okay, in this view, we can just develop a policy network which takes historical queries and the rewards of the queries as input and produce the distribution of the next query of the attack. And by learning the policy network, we can extract many knowledge of the victim model, and such a policy network can be used by other attackers as well. Okay, this method is kind of complex, so I will skip many details. Here's the algorithm pipeline. So we just combine the optimization framework with the hop, skip, jump attack. So you can see we need to do binary search and direction guide near the boundary. You can refer to our paper for details, but because the details kind of rich, so I will skip here. Okay. Besides the black box optimization method and query-based method, there's another series of methods which we actually pay more attention to in recent years. This line of methods utilize the fact that different machine learning models actually share different representations. So adversary examples generated on one model will probably also fail some other models as well. Okay, such an observation that the example can fail other models is called the transferability of the adversary examples, and the model that was used to generate the adversary examples as in white box setting is usually called the source model or substitute model, while the model that was target is usually called the victim model or the target model. Okay, this category of method does not require many queries to the victim model if the attacker is able to collect sufficient label data by outsourcing or maybe insourcing. So by collecting sufficient data, the attacker can simply train a source model to generate adversary example, just like in a white box setting, and pray that such a adversary example can also transfer to some victim model, which is his target. Okay, but this assumption that the adversary example can always transfer is too strong. So actually, in practice, the success rate of such a method usually relies strongly on the transferability of adversary examples, and often we suffer from low success rate if the transferability is not that as good. Okay, so unlike the query-based method, which were mostly developed for reduced query cost, here transfer-based method usually try their best to improve the success rate by improving the transferability of adversary examples. Okay, I will show some of our recent work for improving the transferability in the following slides. Okay, so if you are familiar with the generalization ability of machine learning models, you might see the attack failure of adversary examples to by transferring to victim models is kind of like the generalization failure of machine learning models on some unseen test samples. The difference is that the transferability is just transfer across models, while the generalization ability to test samples is transfer across like samples. Okay, we all know that there's just a long-standing belief that linear models can generalize well, especially better than more complex nonlinear models. So given this fact, we thought that is it possible to somehow linearize the source model to achieve better or improved transferability? Considering that linear models might also achieve better transferability, just like their better generalization ability. Okay, so we did some initial experiments to verify this conjecture. We simply removed the activation layers of some deep neural networks, and we fine-tune such a model because if we remove the activation layers of a well-trained model, then its prediction accuracy should not be that well. So we also fine-tune the model to observe that the transferability of the obtained model along with the fine-tuning iterations. We can see in the figure that the transferability first increased, then it finally decreased to be even worse than the baseline. Okay, the increase of the transferability, we believe it is probably owing to improved accuracy of the model, while the final decrease of the transferability, we believe it is probably owing to another stage of overfitting. Okay, so given these results, we believe that if we can somehow linearize the model without hurting much of the prediction accuracy, we can probably achieve improved transferability. Okay, so how to achieve such a goal? Our solution is kind of simple. We propose to disentangle the forward path of and the backward path of backpropagation, and we then only remove the activation layers in the backward path, which means the quoted gradient of such a method is calculated with the formulation given in the slides. Okay, the attack performance of such a method, which we call it linear BP, is impressive. You can see in the figure that it outperformed many prior works before development of linear BP. And we also observed that linearized later layers suffices to achieve the goal. This is unsurprising because we know that lower layers of different models kind of share similar functionality. They all extract some low-level features from images, for example, edges. So their representation should be kind of similar in semantic space. So we can leave them alone and only linearize later layers, which will do less harm to the prediction accuracy of the method. Okay, another interesting observation of the method is that we observe that it not only improves the transferability of observed examples. Sometimes we also observe that even in the white box setting, it can achieve improved performance than the baseline. Well, which inspires us to do some mathematics, and with some mathematics we actually found that linear BP not only improves transferability but also accelerates convergence. Here are the theoretical results, and the convergence not only lies in the optimization process of generating adversarial examples, but also lies in the process of optimization models. So here you can see that not only the convergence of X is faster, but also the convergence of the parameters, which is W, is also faster. Okay, but I also need to stress that there should be some light assumptions here that the learning rate should not be very large. Yeah. Okay. So given the success of linear BP, we also saw are there any other ways of linearize the neural networks models? We have tried some and found that linear regression actually also works well. A simple solution is to establish a linear regression model which is used to approximate the later layers of source neural networks. We still keep the lower layers of the neural networks unchanged, and we can simply replace the later layers of the source model with such a linear regression model. Okay, although such a model actually doesn't predict as accuracy as the source as accurate as the source model, but it the adversarial example generated on such a model transfer remarkably better than the baseline method. Here's the result. Okay. Besides this method, we also did some other trials to improve transferability. Recall that we assume that lower layers of different neural networks are roughly the same, and we kept them unchanged in our linear BP and the linear regression model. The linear regression model is called ILA++, by the way. But this assumption might be too optimistic. Since they cannot be exactly the same, right? However, even though they are not the same in practice, they might be very similar or might be sampled from the same distribution. There is actually one prior paper shows that the optimization of a deep neural network actually doesn't change lower layers much. So we can assume that they still kept their initialization values, and the initialization of different models actually are given in the same Gaussian distribution. So we can we might think they are from the same distribution. Okay, but if they do come from the same distribution, then is it possible that we can learn such a distribution and attack on the basis of it? Because if we can, then the attack can be considered as attacking an ensemble of infinite many models, and we know that attacking an ensemble of models actually also lead to improved transferability, because ensemble actually leads to less overfitting and more diversity of the model representations. Okay, but how do we model such a distribution, and how can we learn it from data if possible? Here's our first plan. We simply assume that the parameters of many models are actually sampled from the isotropic Gaussian with the fixed covariance matrix, and the covariance matrix actually designed by a hyperparameter. And it is straightforward to expect the mean of the distribution to minimize the Monte Carlo of an integer of some of infinite many models and their laws. And an alternative to such a formulation is that we might also try to minimize the worst case of such infinite many models, just like in the just like shown in the slides. And with some simple calculus, we can also derive that this is actually approximation to the worst case optimization problem, and it is equivalent to the sharpness aware loss, which means if we have the chance to fine tune the source model with the prediction loss along with the sharpness aware loss, then we can actually optimize the distribution as a whole. And by optimizing the distribution as a whole, we can sample infinitely many models from distribution and perform a thorough attack on a sample of these deep infinitely many models. Okay, so here's plan B. In plan A, we assume that the models, the parameters of the models were sampled from the isotrophic Gaussian, which is actually too strong. Here we consider that we might also have the chance to learn the covariance matrix of the distribution. A straightforward way is to utilize a prior method called stochastic weight averaging Gaussian, and we can also fine tune the source model with such a modeling of the prior distribution. Okay, the experimental results are given in the table. You can see that using both isotropic Gaussian and SWAG, we can achieve remarkably better results than the baseline. And more importantly, as I have said, this is orthogonal to what have we done in linear BP and ILA++. So it can be naturally combined with linear BP and ILA++. And here's the experimental results of the combination. And you can see that we nearly achieve perfect transferability to some victim models and nearly perfect attack success rate. Okay, this transfer-based method actually, although we have done a lot of work on it, but actually they they have some restrictions. For example, they require the source model and the target model being trained on the same, or at least a very similar set of data. However, in many application scenarios, such a source model may not be available online, or may not be available even we have the ability to train models. A more practical setting is that we can somehow only collect a limited number of images from a source class and a target class, and with this limited number of images, how can we attack a victim model? Maybe without querying it. Okay, with this setting and with this threat model, we have made some trials. Our first trial is to why not we similarly using supervised learning to train like a binary classification models with even though we only have a limited number of images. Well, the result is unsurprising that the model suffers from severe overfitting since the number of training images is very limited. Well, but inspired by a paper called SingGAN, which actually trains a GAN model using a single image, we consider that is it possible to train like a autoencoder model or generative model using this limited number of images. Okay, but the drawback of the autoencoder model or generative model is that they kind of lack the discriminative ability that the victim model has. So, but without the discriminative ability, it cannot transfer well to the victim model because these two models can be very different. Okay, so then our idea is how about we somehow improve the discriminative ability of the autoencoder. We did some experiment and made some trials. A straightforward idea is how about we use some like self-supervised learning to because we know self-supervised learning leads to kind of discriminative ability and semantic representation of images. Here are two trials of such ideas. We try to use we try to encourage the autoencoder model to solve the jigsaw puzzle and to rotate the image to its original position. But we found that even with such idea and such implementation, we still miss some core information. Is that which is we already know the label of these images, even though the number of images is more. So we propose another kind of reconstruction loss for the autoencoder, which is given any image from any class, can we use the autoencoder to reconstruct a prototype of a prototype from that class? What's more, we can actually use multiple decoders to encourage the model to reconstruct multiple prototypes of the given image. Okay, this formulation and this loss explicitly utilize the label of images, and so the discriminative ability that is injected into the model should be more obvious, and the similarity between the models should be higher. And we indeed found that such a method leads to higher transferability of the generative web server examples. Okay, I think that's all of my presentation. So okay, thank you very much. Any questions?
Thank you very much, Yiwen. So everyone, you can either just speak up if you have any question or write it on the chat, and I will share it with everyone. I can open with a more general discussion about attack transferability. You mentioned that we have either query-based attacks or we can have transferable attacks. But I was wondering, how about techniques that try to learn the model or the training data sets, then use them, then move back to some kind of white box setting by learning the target model? Is it something that that is popular, that can be combined with the others?
Sorry, did you mean that is it possible to combine these two lines of works, right? Did you mean that?
It was two questions, yes. The first one is, are there techniques that try first to learn the model, then attack it in a white box setting? And the second, are there techniques that combine a query and transferable attacks to further improve the transferability?
Well, I think what was introduced at last was the work that we learn a model and then expect it can transfer to the target model. And by combining these two lines of work, actually what was introduced at first, that we learned the subspace of input gradient, it can be considered as a combination of these two lines of work because it utilizes the similarity of models, and especially the similarity of input gradients of models. And it also utilizes queries from the weakly model to search along the search in the subspace to find some like more effective directions. Yeah, but I believe, yeah, of course there should be there can be more combination directions for the two lines of work. Sure.
I see. Thanks. And what are the advantages of? We have a new message.
Sorry, the advantage of what?
No, I was just checking. No, I was just saying the advantage of using Bayesian approach to improve the transferability compared to ensemble models, generate the adversary examples. I guess.
Yeah, I got your question. The main advantage is that Bayesian model actually provides a distribution of models. So actually, it provides infinitely many models for ensemble. Yeah. So but using the traditional ensemble method, we only have a limited number of ensemble models for ensemble. So I think especially the power of such method actually scales with number of models for ensemble. So with the Bayesian formulation, since we have infinite many models, so since we have infinite many models, the performance should be superior to the traditional ensemble-based models.
I see. We have a question from Ranjit. I don't know if you want to say it yourself or I can read it if you prefer, Ranjit, as you wish. Okay, I will read it. So he asked how perturbations at subspace learning are scaled down, as if the learning involves at subspaces. Maybe you can explain a bit more your question.
Sure. I actually kind of get the question. How do it scale down? It's like this. Given these UTs, which are actually gradients calculated on many different deep neural networks, we only need to optimize or search the coefficients for combining these UTs. Given the coefficients, the perturbation of the inputs is just the linear combination of all these UTs with the coefficients. Yeah.
I see. Thank you.
Does this answer your question? I'm not sure. Yeah.
I think yes. Thanks, Ranjit. I was wondering, there are in the defense perspective, if we take the defender, there are techniques to improve the robustness against Y-box attacks. So some of them are mostly obfuscation. But I was wondering if there are lane of thought about how to make the transferable attacks more difficult, defenses against transferable attacks. Maybe probably the mechanism will be different from what is used against white box attacks.
Yeah, well, this is a good question. Actually, we have thought about this, but actually, we have thought about this and actually did some experiments about this. But unfortunately, straightforward idea of utilizing the more transferable adversarial examples for adversarial training doesn't work as well as the traditional adversarial training methods. I think the most problem is that the merit of using more transferable adversarial examples is it can somehow reduce the overfitting problem of adversarial training, right? But nowadays we actually have many tactics for reducing such overfitting problems. So when combined with these efforts, the introduction of more transferable adversarial examples in adversarial training doesn't work as well as the traditional adversarial example. Especially these adversarial examples doesn't lead to very high loss on the source model, because actually for more transfer we have to sacrifice some performance on the source model. Yeah. So which means the merit is reduced, and the merit is reduced, and the dismerit is more is like strengthened. So yeah, the overall performance is not as good. Yeah.
But this is exciting because it means that we still need to find new ways that work and not just use existing techniques.
Sure. Yeah.
Thanks. We have a new question from Martin. Thanks for the presentation. I found your LeanBP paper very interesting and inspiring. A follow-up paper to LeanBP showed that they can achieve better results by backpropagating smoothly instead of linearity. by replacing the ReLU with smoother alternative? Can you comment on the topic? I think that the linearity hypothesis is a bit controversial.
Well, yeah, we haven't tried to figure it out that whether the effectiveness comes from a more smooth optimization procedure or the linear property of the backpropagation process. But yeah, we can try to do some research on this. Yeah. I don't have a very direct answer to your question. To your question about which is correct and which is incorrect, but we can explore more. Yeah.
Thank you. So I guess there are other hypotheses that can be investigated as well, and maybe combined also with the linearity hypothesis.
Yeah, sure. Actually, if we replace it with a smooth version of activation, we don't actually know whether it is more linear or more nonlinear. Yeah, I think that's the key problem that hinders us from explore more about. Yeah.
I see. Any more questions? In that case, I would like to thank you again, Yiwen, for your talk. It was very insightful, especially for someone like me who doesn't know much about transferability. And I would like to thank also the audience for joining us today. And our next talk is in 4 days, on the 20th. We have recorded this talk, so we can stop the recording now, and we'll put it on YouTube very soon.